Excellent. So, good morning, everyone. Welcome. And just for the people who don't know, so I'm having the microphone because we also have the talk streamed live on YouTube, and so it's not for the room. It is my really big pleasure to welcome once more RENATE LOLL here with us in Vienna. Today, RENATE will tell us about something that she is literally famous for, namely her approach to non-perturbative quantum gravity. Last time she was here, for those of you who remember, RENATE was giving an absolutely fantastic public lecture that really managed, and I need to say that with big admiration, really managed to bring across to an absolutely lay audience the fascination of quantum gravity research. If you remember, the panel was really, the discussions were really amazing. People were extremely interested. RENATE's path into science is also a very interesting one. So she did a PhD at Imperial after studying in Germany. Then she went with Heisenberg fellowship to the Max Planck for gravitational physics in Potsdam. And later she took on her first faculty position in Utrecht, and then now and today she is a professor at the Radboud University in Nijmegen. She's also a distinguished research visiting chair at the Perimeter. So basically in a macroscopic superposition between the two locations, something that we of course are very fond of here in Vienna. RENATE got a lot of credits for her work. She's member in several academies. The Dutch Academy of Sciences, there's a name for that, which I had to actually, it's the Royal Netherlands Academy of Arts and Sciences, I apologize. The Academia European, and so on. For her work, she received several awards. One that people know here in Austria, because we have similar things also in Germany, the Vici Award of the Dutch research organization, is actually similar to what we have here as the Wittgenstein Prize or the Leibniz Research Award in Germany. She's also a fellow of the International Society of Gravity and GR. She is a Knight of the Order of the Netherlands Lions. This is one of the, actually I think it's the, I wanted to say it's the oldest, but I think it's the only Order of Merit that the Netherlands have. This is a very prestigious honor for people really standing out in their fields and for public services. And only recently she got the Amaldi Medal of the, which is the, I would say, highest European prize in gravitational physics, and so on and so on. I'm pretty sure there are many more things to come. You're still young, so
no pressure.
No pressure. Let's see what comes next. RENATE, I'm really very excited that you're here, and looking forward to hearing about, I guess, getting introduction, but also hearing about the latest, greatest in the topic. Thanks a lot.
Okay, what could be nicer to wake up completely jet-lagged from my PI superposition and being welcomed in such a splendid way. Thank you, Markus. It's great being here, and of course there is a more important person than me in the room today. You know, I just pointing to Marius. So I was thinking, right, I mean, this audience, you're not an audience of quantum gravity experts, so what's a meaningful talk to give you? And I gravitated towards the blackboard, as you already see. So I will give you a talk with emphasis on the conceptual, and feel free to ask any technical questions you like. I can fill you. I can talk for hours on those things. But I want to keep the big line going, and also understand, from a quantum foundation side versus kind of, where I come from. This is quantum field theory and general relativity, where often similar words are used to mean quite different things in different contexts. And I would say even the word quantum gravity is among those, or things like, causal structure, which is a very popular thing for the likes of you to talk about, but it also plays a really important role in my work. So what I want to, so I will just, as I said, give you a kind of an overview. So I will, since I have only 1 hour, I will not go into any details about very recent achievements, but please ask and interrupt me. That's also what this format is meant to be about. So I talk about quantum gravity from causal dynamical triangulations. So that's the main theme, and of course I will explain what I mean by these various things. So I start by just setting the stage, which is very important. What physical scale is that relevant for? And then it's generally physics near the Planck scale. Planck scale, and for the length scale, this is of course this, I would say, ridiculously small scale of 10 to the 35 meters. Okay, now this arrangement already showing some flaws here. Okay, so and what I'll be talking about is really that we have, with the methodology I'm using, that has really opened kind of you could say a measurement in the sense of numerical experiments window near the Planck scale, and I'm talking about objects, chunks of space-time or quantum space-time that are on the order of 20 Planck lengths across. So there is a health warning in effect for the entire talk, namely that this is a very unfamiliar, from a physics point of view, habitat. Okay, so it's a region where really space-time doesn't look at all like what you're used to. Yeah. So, and of course that really determines both the tools and the results. But so it's so this is a very, as I said, unfamiliar territory. And well, although of course we have to take our cue in a way, from certain geometric notions which we want to see represented in the quantum theory. Of course, many things simply cannot be translated one-to-one. Actually, most of them. And that's in the nature of the beast. So it's not a flaw. This is just because physics is just so different at this scale as we are continuously learning. So in particular, so space-time, I also introduce you gradually to all the abbreviations I'm using, right? QG, CDT, space-time is highly quantum fluctuating. And if you doubt that it is, well, I would say that's a finding. If you didn't believe it was, it's a finding in this setting I'll be talking about. And stuff happens that are very counterintuitive. And space-time can no longer be viewed, as we say, in a perturbative way, as a nice, smooth classical solution to the Einstein equations with little wiggles, which immediately go away when I just look at that from a little larger distance. So it's genuinely a regime now, which people sometimes call, hand-wavingly things like quantum space-time foam. So where things are really not perturbative. Yeah. So so it's very different from a semi-classical and perturbative regime, but nevertheless, well, they're interesting, of course, things we have already learned, but I would even say they are interesting lessons to take away for, well, when one thinks about gravity as one of the fundamental interactions, but in particular as describing structure of space-time. Yeah. So, and how we do it, by what means we describe it, because it turns out we have to really use totally different tools to effectively describe space-time and space-time dynamics when it comes to these to this quantum regime. So so I would say they are already in terms of, what are true degrees of freedom? I mean, things we sometimes struggle with classically. So kind of from a classical point of view, there are interesting aspects to be taken away from this. And secondly, of course, from the quantum theory, of course, it addresses, right? It wants to be a theory of quantum gravity, something we do not yet know. So there is clearly new stuff there. But it also gives us first new ideas. For example, of a very fundamental nature, namely, what do you need as a starting point? You start writing down or constructing a theory. You need to have a starting point. What are your degrees of freedom? On what space are you formulating? And what are the equations? What is the dynamical principle? One of the questions is kind of, what do you minimally need to put in to get something interesting out? And of course, people build all kinds of fantastical models that are supposed to work at the Planck scale, or maybe at trans-Planckian scales. Yeah, but then when it comes to saying, okay, but how does this relate to gravity as we know it, general relativity as we know it, that tends to be very, very difficult to make the bridge back to low energies at large scales. Okay, so and that's actually one of the key, you could say, tests you apply to a so-called non-perturbative model of quantum gravity that, on appropriate length scales, at least some classical traits have to be recovered. Okay, so here is a preview. So that's the program of the rest of my talk. So firstly, say a little bit more. What is quantum gravity? Secondly, I'm picking out, it's a very complex topic, but I'm picking out what I call 3 key challenges. For quantum gravity. Okay, no question mark. There are definitely challenges, but it's a sub-selection. So, and then I will say how CDT addresses those challenges. And I would say resolves them. So that's the main part of the business. And so there's a new keyword I've invented to talk about this, which is form follows function. And that's not, I don't abbreviate it, although it would be very nice, the FFF. So what I mean by this, so it turns out the way these 3 challenges and others are addressed comes really as a package with kind of the toolbox I'm using to do this description. And I will argue to you that the toolbox is maximally well suited to addressing some of these key challenges. So it's kind of the whole thing comes as a package, and in this sense, the way, if you like, the variables I'm using, the formulation I'm using, optimally fits the way in which I'm resolving these challenges. Okay, and then we have for your questions. And as I said, I encourage you to ask questions in between. Okay, so then we get started with point 1. And let me give this very conventional answer, right? What is quantum gravity? Well, it's this unification of general relativity, the theory, our best theory of gravity and space-time, with, this is how I would formulate the principles of quantum field theory. Okay, so, and let me just write down a few things and then say more about it. So we unify general relativity and which I will in the following abbreviate as GR, so according to Einstein, of course, with the principles of quantum field theory. So, and of course, kind of the field is important because we are talking about infinite dimensional, systems. So things are, of course, often a little bit difficult and have a different flavor from a finite dimensional quantum system. So that's also why I'm not saying, you know, quantum theory, of course, but of course it is in part quantum theory. So what are the important lessons, right, from Einstein? The first one is, of course, well, because gravity is universal, I can think of it, I mean, and gravitational forces, etc., as coming from some intrinsic structure of space-time itself. Yeah, and that means empty space-time, if you like. So gravity is, in the Einstein sense, according to Einstein, space-time curvature. Yeah, so the way in which space-time has this non-trivial structure is just, you know, we encode then the effect it has on matter that moves, say, in space-time. And of course, really, space-time is dynamical. So that's the main feature, really, which distinguishes, I mean, which is kind of a consequence of this. And of course, there are many phenomena. The expanding universe, right? Pre-Einstein, I mean, was unthinkable. Anyway, Einstein himself thought, right, the universe, of course, doesn't move. It's there, you know, it's been put there by someone, and it's there forever. But of course, now we know better. It does actually move. You know, we have gravitational waves that were detected more than 10 years ago, which of course is epitomize, you know, space-time moving, if you like, and undergoing classically certain fluctuations. So this is a very, very successful picture of describing gravity, and is very well tested in its domain of validity. Yeah, so this is a really good theory, and plus it is, you know, mathematically very beautiful. Of course, there are aspects in this description which are bothersome, and that brings us back later to the, you know, story of the 2 degrees of freedom. So what do we have here? Well, I would say, well, of course, you know, all our other fundamental interactions turn out to be at their heart quantum theories. So kind of one of the big lessons of 20th century physics is that, you know, all kinds of matter we know of, if you look close enough, or, you know, it's sufficiently high energies, has to be treated according to quantum laws of motion. So there are quantum theories, right? So we have here quantum laws of motion. And of course, with everything that this entails, and, you know, I'm in Vienna, so I don't have to tell you about the superposition principle, or, you know, the uncertainty relations, etc., which of course are incorporated also within the standard framework we have built up of quantum field theory. And our best theories, right, of the standard model, they're all quantum field theories. Yeah. So that is very suggestive to say, well, look, all of physics is quantum. If you just look at it in the right way, and only a minority of people would maybe contemplate that it's otherwise, but I don't want to go there for today, and rather take this point of view, which leaves, of course, kind of a big hole in our understanding of the 4 fundamental forces, because we are still looking for a fundamental quantum theory that underlies Einstein's theory of general relativity. Yeah, and well, it's also plausible, kind of by the universality, I would say, of gravity, which I've commented on, and kind of, yeah, universality of the presence of quantum features of matter, which of course, by, you know, matter coupling universally to gravity, gives us at least a very strong argument that also gravity should, at its heart, be a quantum theory. So that is so then the key question. So what is that theory? What is the fundamental quantum, presumably field theory, underlying general relativity? Okay. So, of course, we have gotten away for a long time without this unified theory. And it's a justified question to ask, well, do we ever need it? Because somehow GR seems to pertain, to large-scale properties of our universe, right? How do things move on very large scales? The planets, etc. Or like the, what we describe in cosmology, the large-scale properties of our universe, and maybe nowadays gravitational physics, right? Black holes, how they spiral into each other and give off some signals. Whereas this is very, we tend to associate with a very microscopic or macroscopic for you guys, right? But still macroscopic and kind of, scale of the universe are very, very far apart. So is there, you could ask, is there a regime where these two things, talk to each other and are potentially in conflict with each other? And the one that I will quote here is really kind of physics near the Big Bang. Yeah, just going back in the history of our own universe to further and further back, and as we now believe, the universe was smaller and smaller and smaller. So if you go back, it becomes denser and denser and denser, and with very high energy scales, very short length scales. And eventually, the laws of general relativity will simply not be valid anymore. And then, yes. I mean, I would view it really in the same way as we view QED and classical electrodynamics. Yeah. So I would call that is the theory. Yes, please. Yes. Yeah. Yeah. I'll get to this point. Yeah, that's right. So quantum field theory, I haven't said on a fixed background. That is, of course, the standard setting for relativistic quantum field theories. You're completely correct, but I get there. That is actually more or less my my next point. So again, here to say, this will certainly have to say something about this regime, this very remote regime, in a way. And space-time will not be nice, and it will not be smooth, but it will have these quantum fluctuations. But what is it? We typically just wave our hands about it. So, but I just want to write down the key word, although I have already said it, which is non-perturbative. So non-perturbative regime, which I abbreviate NP. So, and as I said, people sometimes call this now quantum space-time foam. Space-time foam, but this is just a stand-in for really not understanding what becomes of the nice space-time. So people draw all kind of bubbly pictures, and well, as a side remark, myself and a group of people from my group, we are just looking at measures of understanding what the microscopic, non-trivial topology might be of this quantum space-time. So yeah, I will not be able to talk about it today, but it's really a test. Is there really anything? So what we're looking at are, the Betty numbers in a quantum context. I won't say more about it, but this is really a test of, is there anything to this foam picture, or is this just free fantasy? I think it's probably free fantasy, but it doesn't mean that there isn't something very interesting happening near the Planck scale. Okay, so very non-intuitive. So I have given most of my health warnings, and also, well, this already indicates that somewhat implicitly from what I've said. So in terms of mathematical tools, one expects to need to go beyond the mathematics which underlies general relativity, which is the differential geometry of smooth pseudo-Riemannian spaces. Yeah? And this will turn out to be the case. And in fact, what has motivated some of the structures we are now using in the quantum theory comes from extensions where mathematicians talk about more general non-smooth metric spaces. And there's much that can be done there. And it's a big topic of studies within mathematics. So that's another kind of interesting connection there to interesting things that happen in parallel elsewhere with a completely different motivation from, how we come to it from quantum gravity. Okay, let me turn to point 2. So what are the 3 key challenges I want to talk about? So the first one is the principles underlying these 2 kind of theories or setups we want to combine, are they really incompatible principles? And really every popular article I've seen written about quantum gravity kind of starts from this as a premise, then explaining what is the newest theory of quantum gravity, whose ambition is obviously to combine the 2. So there is a little bit of a, these 2 things jar sometimes. So what is the key thing I want to zoom in on? It's the question that you already mentioned, Czaslaw, how one views space-time here and here. Yeah. So here, space-time is just a flat background. Yeah. Of course, there is a metric structure, a relativistic quantum field series, yeah, where you work with Minkowski space. Of course, it has a metric structure. You know what distances are, what space-time distances are. So, but it's kind of uninteresting from the point of view of GR because it's flat. So it's structureless in a way. Whereas here, of course, in GR, yeah, we already seen, space-time is dynamical. So the metric is just the dynamical degree of freedom of this theory in the way we usually write it down. So really, the thing one may ask, well, are these 2 things so separate that I cannot kind of combine them in a meaningful way? And the answer is, of course, and hopefully no. Yeah, otherwise we wouldn't be trying to come up with a theory of quantum gravity. So here, my second point is that in this very remote regime, this non-perturbative regime, there are why do so few people go there? Because there are very few computational tools that would allow you to say anything beyond perturbation theory. I mean, perturbation theory we know, right? For instance, for the path integral, which I'll come into later, well, it's kind of turning a crank, yeah, and spitting out, writing down amplitudes in powers of h bar. But at the moment where perturbation theory fails, what do you do? So how do you compute? And, well, as an extension of that, what do you compute? Because I said already, this is a very unfamiliar habitat. So what are meaningful questions to ask? Yeah, so that means, what are the observables in a way? And won't they be very different from classical GR? Well, potentially, of course, the answer is yes. And so what are they? So in my third point, and that is often somewhat underemphasized in discussions, is a question of uniqueness. Okay? So uniqueness means, I come up with some theory in a theoretical way, some way, or computational way, but how many free parameters does it have? If it has very, very many free parameters, well, that makes my life very difficult because currently we have 0 experiments to fix these parameters. So if I have very many or maybe even infinitely many free parameters, then my theory has 0 predictivity and can predict everything. It's of course a very nice feature to have, but that's not usually what we aspire to. So we want a little more structure than this. And I would say we've been down the rabbit hole of non-uniqueness since the 1980s with kind of what string theory turned into in the end. It's just an extremely rich framework, but with so many freedoms, ambiguities, and free parameters that there is no predictivity. And then ultimately one has to say then it's useless. It's a very harsh, I mean, at least for the purposes of arriving at a predictive theory of quantum gravity. So, and that's of course the challenge and what we'd like to do. Any questions up to this point? Or comments or clarifications? Good. So let me say, make a very brief excursion to QCD. Okay. And you will see in a second why I do this. Okay, so this is quantum chromodynamics. Why do I do this? Well, it comes from really thinking about this point first. Where else in the context of quantum field theory do I find myself in a situation where these perturbative tools are not sufficient for me to understand and derive predictions from the underlying theory? So, of course, QCD is a theory we know much, much, much more about than quantum gravity. Yeah? But it has a low energy, non-perturbative sector. And the only way of understanding what this sector is to, as we say, put the theory on the lattice. So to use lattice methods. Okay, so to actually computationally get there. So what does one do? The key idea is to approximate flat space-time, so Minkowski space-time, flat space-time by a four-dimensional, usually cubic lattice. Okay, you would say, ooh, how very uninteresting. Well, it's not. So it's extremely useful. So here is my little drawing of the lattice. So of course, it's an approximation of flat space-time. Yeah. So this is a completely regular lattice. Imagine it's four-dimensional. Yeah. So and the interesting things are kind of the vertices and the edges or links of the lattice. Yeah. So here, and here. And all your quantum fields will now either live on these edges or these vertices. And what is very important here is that how fine-grained the lattice is determined by a parameter we call little a, and that's called the lattice spacing. And that just tells you how far the lattice vertices are apart along these edges. Now, so what's the benefit of this? Well, it discretizes, this quantum field theory, which of course it's kind of full of infinities, right? In any sector, but also in this non-perturbative sector. So it kind of discretizes the field space you're working with, because fields cannot live anywhere, but here they are forced to live on these edges, so that makes your life simpler, and you typically you make this lattice finite, because you want to work with it on the computer and run kind of Monte Carlo simulations. So it's really a classic case of a regularization of the theory that makes it finite and computable and well-defined. But of course, so this discretizes the quantum field theory to make it computable. And what one then computes is, what is the quantity one computes? It's really the path integral. Yeah? So that's the key, you could say, the dynamical principle. But applied here to this context, if I would, so Z with me stands for path integral of all kinds. In the continuum, before I put it on the lattice, let's imagine I was working in a pure Yang-Mills theory, so no matter, no fermions coupled. Yeah, it would be some kind of functional integral over the space of all gauge potentials, A mu, and then you have here e to the I s, the Yang-Mills action, which is some functional of these gauge potentials. And of course, it's a gauge theory, so there is some gauge group acting. So let me indicate it like this. So these square brackets indicate, I'm just integrating just over equivalence classes. So there is some gauge redundancy here. But this is the thing one wants to compute. And then one discretizes these A-related variables to lattice variables. And then this has then a lattice form, which one can then compute on the lattice. And one of the beautiful things of doing this, according to Wilson, who is of course extremely famous for many things, is he had found a way of keeping exact gauge invariance, although this is a discretized way, a regularized way. If you are familiar with it, so gauge transformations still act, but they act only on the discrete vertices and in an exact manner. So that's a beautiful, this is just a side remark, but so now one can compute with this, and of course the crucial thing is then one takes the limit as A goes to 0, because one wants to remove the regulator, and one wants to recover a certain continuum theory. So one uses Monte Carlo methods for doing this, so let me cut a long story short. So this has been super successful since the 1980s, just to say, super successful in actually computing properties of the spectrum of the underlying theory. Yeah, here I do it just for pure Young modes, but of course including matter is important, and fermions. So one can now compute things which one in a way can directly compare with outcomes of experiments at CERN, etc. So this is amazing. And there are no other tools which allow us to do anything like this. And this is, of course, a huge industry with a huge community associated with it. If, I would say, in quantum gravity we were at a similar stage, that would be amazing. Okay, and now comes your question. Yeah. For each observer, exactly. You pick an observable, and then you will measure it, and you will then make A. So you keep doing the measurements while you shrink A to 0. Effectively, what it typically means is you send the number of building blocks to infinity, well, which of course is impossible on a lattice, but you make it large. And you look systematically at the scaling behavior of how this behaves. And only, of course, with very specific ways of finding such a scaling behavior, which is not guaranteed, will there be a continuum theory you're approaching with these results. That's right, and that is a very crucial thing. And I will get back, you're asking such good question, I'll get back to it in the, in the remainder of my talk as a very important issue also in the quantum gravity case. So not to stay in the discrete, for the discrete, with the discrete objects, but to generally take this non-trivial continuum limit. Okay, now, so I said, well, this has been known. It started in the 70s. It started really rolling in the 80s, also with this work by Wilson. And people from the very early days thought, well, gravity, let's do the same thing. Let's put gravity on the lattice, on a lattice. Okay, so, but how to do this? You can do it in a very naive way, and that's what people did for a very long time. I was struck recently because we had the 70th birthday conference for my colleague and friend Lee Smolin, and for that I prepared a little talk, and I went back to his very first paper. He wrote as a grad student at Harvard, and it's from 1979, and it's about putting gravity on the lattice, quantum gravity on the lattice. And in one of the first paragraphs it says, well, yes, I think this is a wonderful idea. We should all do this. But there is a clash of fundamental principles because space-time is dynamical, and these lattices, they're just flat. And they're not dynamic, and they just sit there. Well, because they're just approximations to flat Minkowski space-time. So it's fine for relativistic QFT, but it's not fine for gravity. And it says, well, what we really need is dynamical lattices. Unfortunately, we have just no idea how to do it. Okay, so now we are 40 plus years later, and now we know how to do it. Okay, so that's the new thing, and that's the part about the dynamical in the CDT story. So and that's in a way the key to many other things. So let me just describe to you three. In a nutshell, the ingredients I use to try and emulate a dynamical version of this, and this is just what CDT is about, with a few other things thrown in. So what are the building blocks? So we talk about building blocks. So we are not using squares, although this is just a choice which is not so important, but we are using a bunch of triangular shaped building blocks, and essentially they're all identical. And they're called simplicio. Simplicio is just a stand-in for triangular, but in higher dimensions. building blocks. And I was going to draw one for you. So, oops. So the elementary building block is a 4 simplex in 4 dimensions. And it's an object. Well, it's a generalization of a triangle and a tetrahedron in 2 and 3 dimensions. But it's something that has, 5 vertices, yeah, and 10 edges. And of these edges, we distinguish between time-like edges. I should maybe draw it in some way. Well, it's a 4D thing, so there's just no way to draw it on a blackboard. That's not utterly confusing. Sorry. So, and here I need a couple more. So, and I have here below, Daniel will correct me if I'm wrong. Well, roughly speaking, this is one of my building blocks. So you think of them as an analog of my 4-dimensional cubes. So it's triangular, but really that, as I said, this is not so much the issue. It's convenient, but also it's a piece of Minkowski space. So I know everywhere it's by definition flat on the inside, this building block. So you should think of it as cut out of flat Minkowski space. So it has a trivial structure, it's just flat on the inside. And if you postulate such a building block to be flat on the inside, then its geometry is completely determined by giving all the edge lengths. So here we have time-like, we discriminate between time and space-like edges. Okay. So these are my building blocks. So what is the rule? In order to obtain a space-time that will enter into the kind of path integral, as one of my things configurations I'm integrating over, I will regularize these to become lattices, and there will be triangular lattices, and this will be kind of the elementary building blocks. And to get one of these histories or configurations, I'm allowed to glue these things together, of course, so that the metric properties match. So I have to give you kind of gluing rules, or let me call it connectivity data. Yes. So there are allowed ways and not allowed ways to glue them together. And one of the key things, which again I will have not very much time to talk about, is that kind of the light cone structures they match during the gluing. And not only they match, so it's not that a light cone in one matches collides with a light cone in the next building block that points in a different way. No, there's a kind of an overall flow, yeah. So that imposes a discrete version on what classically we call global hyperbolicity on my curved space-times. Okay, so what does it mean? What is the most important thing that implies? It's if I monitor my now triangulated space-times as a function of we have some kind of notion of proper time that proceeds in steps, then the spatial topology is not allowed to change. Yeah? So, of course, if I allowed arbitrary gluings of these things, well, it would branch, many, many more things are possible, but by hand, I'm throwing out these things that don't have a nice causal structure. So, and I'm doing this by hand, yeah? And I'm just telling you, if I didn't do this, then I would revert to something that's basically called Euclidean dynamical triangulations, which hasn't really seen anything interesting. Yeah, so then I'm sitting in a different universality class. Okay, so where was I? Okay, these are my building blocks. So there are certain gluing rules by which I put them together, causality constraints. And note, so one thing is, I should say, how can these flat objects capture curvature? Yeah? So they capture curvature through the way in which I'm gluing them together pairwise, along their so-called faces. So these faces here are 3-dimensional tetrahedra, right? So I'm gluing together 3-dimensional tetrahedra. And in a way that's easiest explained in 2 dimensions. So imagine I'm working in, let's say for simplicity, Euclidean signature where all my building blocks are equilateral two-dimensional triangles which have, 60 degrees angles everywhere. So how these building blocks, again, are flat in analogy to what happens here, but this represents a piece of curved space-time because here there is a deficit angle. So if you add up the angles here, they don't add up to 360 degrees, but 60 degrees are missing. Yeah, so pi over 3 are missing, and that's a so-called deficit angle. And what that means is there's curvature at this point, yeah, in a kind of singular way, but its curvature I can detect, for instance, by parallel transport. So that's the old idea that already is used in Rete calculus for how piecewise flat spaces or spacetimes really are a stand-in, carry curvature. So, and that's true for any signature and any dimension. So this is why these general gluings or connected objects I put together from these carry curvature, okay? But already note that from a point of view of classical theory, these are not nice, smooth spaces. So they sit full of curvature, curvature singularities, caustics, and of course what we'll do in the end, we take some continuum limit where kind of these edges kind of shrink to 0, and then it's a kind of, these are objects that are filled densely with kind of curvature singularities. So they're extremely non-singular, kind of nowhere differentiable objects. And if the analogy with the path integral of a non-relativistic path, a particle means anything to you, if you do it via Feynman-Hibbs, then you'll find that generic paths that contribute to your path integral, your superposition, are nowhere differentiable paths. So, and there's no, that's just what it is. That is what gives you the Wiener measure. And we are doing kind of a 4-dimensional analog of this. And it's no surprise that very, very singular objects appear in the carrier space of the path integral. It's to be expected. It's not a flaw. It, of course, has nothing to do very much with classical way of thinking about space-time, but that's, that's what quantum theory is for you. So, yeah. Yes. Yeah. Yeah, exactly. So, yes, very good. Okay. So, the in analogy to here, what I want to compute here as my key dynamical object of interest is the gravitational path integral. So again, for simplicity, let me just look at pure gravity, because of course already, pure gravity is a very non-trivial and non-linear theory. So what is then the analog of this formal path integral for gravity? It's the functional integral over equivalence classes of space-times. What are the equivalence classes? Is, let me call M the underlying manifold. I identify, of course, manifolds when they are connected by a 4-dimensional diffeomorphism. So my real kind of space of physical degrees of freedom is this quotient space. In a similar way as here, you're factoring out, as one says, right, by the local gauge transformation. And here you have your e to the I s, your favorite gravity action, which of course is a function of g mu nu, some local function, right? So some action. So this is the thing now we'd like to compute. So what does it become in this regularization? So this is totally formal. Why is it totally formal? Because you haven't said how you parameterize this space, for starters. You haven't said how you implement this, how you get rid of this huge redundancy. You haven't said what your measure is. You haven't said how you deal with all the infinities this quantum field theoretic path integral has already perturbatively. But we have to go beyond perturbation theory. So you haven't said how you can evaluate, well, this is a complex object, right? We know nothing about the convergence behavior, so we need a Wick rotation. So what is the Wick rotation? No one knows what the Wick rotation is. So, okay, so it's a whole, this is, this competes in the most ill-defined object you write down in theoretical physics. I'm sure there are more, but it's pretty high on the list of things that are, they're just so formal. So this is a statement of intent. Yeah, this is how to think about it. So now, the trick is here. I have now to convert it in a regularized way to something that is well defined. So where I can just do the integral. Okay, so that requires a bunch of steps. One of them is this regularization, and then already you come to a much a better defined quantity, and it will be a sum over all, let's say, distinct T. So where T is a causal triangulation, a Lorentzian signature triangulation I get from these rules, right? I haven't been too detailed about what those are. And what then turns out, there's a simple kind of a measure factor, which is for a given such triangulation, it measures how many non-trivial discrete symmetries there are, mapping the thing onto itself. These tend to be extremely rare. So for all practical purposes, think of this as 1. And then you have e to the I, s. And you're right, you have then to give me a way of, here, of course, if you do that here in Young-Mills, you will have a lattice representation of what your f squared, f mu action is for pure Young-Mills. And here you have, say, the Einstein-Hilbert action, typically. And you have now to rewrite it as a function of the variables that describe pure lattices. So, and we know how to do this since Reggie, if you like, because he has given a form of the gravitational action where the edge lengths appear. And once you know the edge lengths and you know how the building blocks are glued together, you can compute all lengths, you can compute volumes, and you can compute angles that contribute to curvatures. So everything is then expressed as a function of properties, of the connectivity data in these edge lengths. So that's the trick. And okay, this has still the I in there. And now it turns out, although no one in the continuum knows of a good Wick rotation or an analytic continuation to get rid of this I, this approach has a well-defined analytic continuation. Okay, that converts this to then. Okay, now I'm doing something nasty. So it converges this to that, and this here now are kind of Wick rotated, if you like. So my map is a map on actually the length assignments. That is what the analytic continuation is about. Under this analytical continuation, then every kind of causally ordered curved space-time in Lorentzian signature is mapped onto one in Euclidean signature, okay? Which is also a curved space-time, but it's Riemannian in nature. It's a piecewise flat Riemannian manifold. And then it turns out this is then what I can evaluate numerically with my Monte Carlo simulation in a totally analogous way to what I'm doing here in QCD. Okay. Now note that the variables, yeah, okay. Yes, so it's so it's very well motivated. So in the continuum, it's you can think of it as a remnant of kind of the de Witt measure in the continuum. There is a distinguished measure on the space of all metrics that is sometimes evoked in the continuum when you try and do this. And this is a de Witt measure. It's a kind of a local measure that depends on G mu and not its derivatives. And it weighs, it gives a lower weight to geometries that appear here that have isometries. So it's kind of interesting. So it appears then as an extra weight. So they have less weight in the path integral. So of course you're integrating here formally over generic G menus. But of course in this huge space there sit very rarely these points which have isometries. That is flat Minkowski or de Sitter. And they're very special. And however, they get an extra suppression in this integral. And this is mirrored here, where I said if your triangulation T has extra symmetries, then you divide out by the size of the symmetry group. So if it's an order 2 group, you divide by 2. If it's an order 10, whatever group, you divide by 10. So there is a relative suppression here. So this is, trust me, so it's well motivated in a way and from certain geometric properties. So So that's what it is. So this magic thing, of course, it looks now very simple. Yeah, but of course, the dynamics is now that of all these configurations, or all these, regularized triangular. It's a superposition of these triangulated regularized spacetimes. So this now you try and evaluate with your Monte Carlo methods. And of course, then this limit, well, to which I'm getting now, will be very important. So here we have a Wick rotation. So there exists a kind of Wick rotational analytic in CDT. And it's very, very important because no one else has a Wick rotation in their quantum gravity models. So, and our choice of fundamental variables, which, by the way, are non-redundant, so that's kind of very important. So, so now the way the connectivities and these length variables, there is really kind of a one-to-one map. Different connectivity really maps onto a geometrically distinct object. So what we are doing de facto is my variables already are variables on the quotient space here. Yeah, and so the length variables, they are, of course, they are kind of geodesic length variables. And the beautiful thing is they're kind of local, yeah, but they describe the geometry in a unique way. Of course, that doesn't make quantum gravity kind of local, because we will see in a second that all observables are still very non-local, as one would expect. But it's a very beautiful and convenient choice that should be contrasted with the standard x g mu nu of x choice. We are shackled to, I would say, in the continuum. We are forced to, when we want to describe dynamics of classical GR, we are forced to introduce coordinate systems locally. And we don't feel that's something undue. We like it, because then we write down all our fields and our curvatures, G mu nu, as a function of this, and then we write down differential equations which we solve. Is there anything not to like about it? Well, it's this huge redundancy, because if you perform a diffeomorphism, then these G mu nus look totally different. So staring at entries of G mu nu are generally not necessarily a good way to understanding what the actual physics is. And of course, people have been misled in many ways. In the classical theory, what is physics and what is gauge, or what is just coordinate transformations. So what I'm emphasizing here is that in these bare bones geometric variables by which one describes these regularized, discretized spacetimes, these variables have a much more direct meaning, and their diffeomorphisms no longer act on them. They're just length variables, and they're geodesic lengths, and then you have these connectivity data, and they are just part of geometry. If you know those, you know everything in a non-redundant way about the geometric properties of one of these things. So it's a beautiful thing, these piecewise flat things, and of course it goes back to 1961 paper by Regge, right, who was trying to use similar variables to numerically, classically describe GR without coordinates. That is the title of his very famous paper. Okay, so very quickly, so what does one do? Well, the path integral. What does the path integral give you? Not very much, but the next thing is, of course, observables, right? How do we characterize now the theory with observables? So what is an observable? So very, very briefly, observable is some, operator. Yeah? So, and what we compute when we have the path integral, we compute its expectation value in the ground state. At least that's one of the things we compute. And once you're given the path integral, right? So I'm choosing now again kind of a formal continuum language, because it's a little bit more familiar to illustrate what I'm doing. Sorry, this is of course the whole point. So O is just some function of the metric e to the is graph of G mu nu. Okay, so, and of course the physics is in these observables. And to understand what quantum spacetime is, I evaluate suitable observables in this path integral. And that's again something I can now just compute on the lattice. Okay. I can, my time is kind of running out rapidly. Let's see what makes sense. I can give you some examples and just point out what the issue is in quantum gravity. So, of course, in quantum gravity, because of this gauge invariance, local objects are not, some field quantity at the point x is not an observable, but all observables tend to be global, and they tend to be space-time averages or integrals of, say, a local scalar. And all the things we have, almost all the things we have studied are of this nature. So now we have these very nice local variables, as I told you, but the observables are still non-local. And so which types of observables have we been able to look at to understand what is now the physics of what we are seeing here, the near-Planckian physics. So just some very brief observables. So we have looked at dynamical dimensions. So dimensions is a way to characterize a metric space, like the ones we are getting here. So Hausdorff dimension and spectral dimension are the two most prominent ones. And you measure them, for instance, the spectral dimension, you measure how far does a random walker get in a certain diffusion time. And from that, you deduce kind of an effective dimension this diffusion process sees. And this you can set up of the ensemble of geometries that underlies here. And you find this very remarkable thing that there is a non-canonical result at short distances. So if you measure the spectral dimension of the space-times, or kind of the dynamical non-perturbative ground state that this path integral generates for you, and which we measure on the computer, then it has not a dimensionality of 4 on short scales, but something that is 2 up to numerical error bars, which are quite large in that case. But nevertheless, it's a quantum signature which has nothing to do with classical GR. In classical GR, the dimension is 4. No matter what you do, there is just no arguing with the 4. Because you have huge quantum fluctuations, other things are possible and radical things can happen. And even the dimensionality, kind of the effective dimensionality of your space can change. But however, what is nice, if you look at the same spectral dimension kind of on larger scales, where of course they're not macroscopic but larger, they are compatible with an asymptotically going to 4, which is a classical value. And this is beautiful because you think of it as that is an indication that this thing has actually a good classical limit. Okay, so we have look at these things. We look at kind of the shape of the universe or of space-time, and what we look at there is the three-dimensional volume of the spatial slices as a function of kind of the proper time with which I propagate through these histories, and this now displays beautifully this expectation value, kind of what this we call a volume profile of a classical de Sitter space. So what this is basically equivalent to giving you the scale factor of the universe. That's what one uses in classical cosmology all the time. If you take the cube of that, it's basically the 3 volume. And what we are finding here is a non-trivial behavior as a function of time, of proper time, and it can be very exactly matched to that of a de Sitter space. So this is totally remarkable. We have these super quantum fluctuating superposition of these spacetimes which are generated this way in this very non-perturbative regime, and they conspire in such a way that on sufficiently large scales, and this shape is of course a very coarse-grained variable, it doesn't tell you anything about local geometry at all, it can be mapped to the behavior of a classical solution to the Einstein equations with a positive cosmological constant. So that's kind of an amazing thing. What we are currently doing is stuff like we are looking at more local things. So in particular, I want to mention we're looking at 2-point functions. 2-point functions are correlators. Okay, so you you sit in your space-time and you wiggle something here, and you look at what happens here. the difficulty in quantum gravity being anything just located at the point x doesn't make sense in this sum over space-times. Yeah. So in the same way as the field at a point x doesn't make sense, it's not diffeomorphism invariant. Also, a correlator that depends on 2 points doesn't make any sense. So in order to make this into a diffeo-invariant quantity, what you have to do is you have to fix this to a certain geodesic distance, dg. You have to fix that, and then you integrate over all x and integrate over all y. And in this way, you arrive at a diffeo-invariant 2-point function. And, well, of course, this is not a very global object because you've done all these, integrations, but it's a well-defined object which you study as a function of this distance. So you study, you look for like, a short-term behavior, maybe a long-term, a long-distance behavior, maybe some fall-off, and you look for characteristic behavior in the sense of, some scaling, universal scaling variables that dictates the behavior of this. And moreover, what is beautiful about 2-point functions, if you're thinking about, what might be a phenomenology I might connect to in this, I think our best bet is kind of early universe cosmology. So, and what are the key things that everyone works with in cosmology? Well, they're 2-point, 3-point functions. Yeah, just looking at something wiggles in the sky here and there, and let's determine this. So, in the best of all worlds, we will be able to, from totally, first principles quantum gravity, to detect some universal behaviors that pertain in this very non-perturbative regime to the behavior of these 2-point functions. And what I have in mind is something like curvature correlators. I mean, something that is really geometric. This is really very, very, very tricky to measure. So I think that, well, it's a major undertaking, but something we are actively looking at. We can do this in 2 dimensions. In 4 dimensions, it's much more challenging. Will we be able to see a clean signal at all? Is unclear, and will we be able to push it? But potentially, it could give me a way to say, look, here, this is a certain behavior of my 2-point function. Of course, I have to think of many other things, right? This is now very early universe, pre-inflation. How would this propagate to the universe at later times, or whatever we are observing in the CMB? Well, that's a different story, So, will it survive this signal? One doesn't know, but it's a road to say, here is a potential way of genuinely connecting to phenomenology, and of course that's something we are very much missing. So here, just a few technicalities need to be filled in, and obviously conceptual issues that come with this, which I don't have any time to talk about. Right. So coming back to my form follows functions. So I've sketched to you how really this framework addresses some, I would say, conceptual, what are called key challenges for quantum gravity. Yeah? And in a way where it was very crucial, my choice of how I parameterized kind of this configuration space, how I'm dealing with diffeomorphisms. What are my diffeomorphisms? They just become relabeling symmetry. So you could say, where have they gone? Well, I have to, like in classical theory, I have to point to x points x, where my tensors live. Here, I'm in this non-smooth framework, there are no tensors anywhere, but they're length variables, they're volume variables, and they're attached to certain places in my triangulations. So, of course, I have to give those places names in order to work with them in the computer. But then they carry an exact relabeling symmetry that's very easy to take care of in the way we set up the computations. So it's a beauty kind of, it's even better than what Wilson could do for lattice gauge theory, I would claim, is what this does for gravity on the lattice. On the uniqueness question, so what we are doing currently is we are working with 2 free parameters that appear, so this thing, before you take the continuum limit, a goes to 0, is a discrete regularized object. It depends on bare coupling constants. Yeah, and so there are 2 coupling constants here, which relate to some scaling between time and length variables, but also to the Newton constant. So wherever we play this game on the computer, we are setting these parameters to certain values. And of course, they're not physical, they're bare couplings, so they're chosen by hand, and they undergo renormalization in this story. And the renormalization happens because it turns out that this, viewed now as a statistical system after the Wick rotation, this has a phase diagram of these bare parameters, which has second-order phase transitions. And the existence of a continuum limit, that gets me back to your question, is dependent on there being these higher order phase transitions in my phase diagram, right? It's really like a condensed matter system. It's really like, phase diagram of the Ising model. Yeah. So I have here my bare coupling constants. They're called kappa and delta. So I'm studying this system, and I scan my parameter space, and I look where interesting things happen. So I have various phases. One of them is interesting, is the zeta phase where we see this thing. But there are also kind of lines, transition lines, which are of second order. What is the relevance? When you see lots of arbitrary ingredients go into setting up a lattice formulation. My choice of lattice, my choice of discretized action. How do we get rid of all these parameters that parameterize these potential choices, which we hope will drop out somehow in the end, because it shouldn't be relevant that we use triangles and not squares, just to say one thing. Yeah? Or the minute details of the choice of measure, of the choice of discretized action also shouldn't matter, because these are not physical things. They're just kind of approximation to some eventual continuum theory. So this is assured if you have a second order phase transition in your system that holds for, this is just statistical mechanics lore. And if you approach such a second order transition, if you're lucky and certain scalings work out correctly, in that case, the system, the continuum system you get while simultaneously regularly renormalizing your bare coupling constant appropriately, then has properties that are universal and that do not depend at all on discretization details, like the choice of the building blocks. And for it hasn't been seen in other models of quantum gravity, our phase space has second order phase transition. So they're natural candidates of genuine continuum theories where your setup forgets about the discretization details. And you see, that is what we want, because we want somehow these triangles to be even much smaller than the Planck scale, so that the Planckian physics we get out of it is kind of, relatively unique or parameterized for very few. In our case, currently just 2 parameters. So that's great. So that answers to some extent the uniqueness question. So if this is correct, it's really just depending on 2 parameters being kind of fine-tuned or chosen. And that's good. That's much better than 10 to the 500 to say a thing. Okay? So in a way, so this box is ticked off, but the continuum, the way you reach a continuum limit, so is really important. So if you just, people who insist on fundamental discreteness, in quantum gravity and say, okay, such building blocks, clearly this must be the Planck length and you shouldn't go to any shorter lengths. Well, unfortunately, then the physics you're deriving will depend in an essential way on how you choose arbitrary, how you choose the dynamics and the building blocks at this scale. Of course, on classical scales, it may forget about it, but our central aim is not to rederive the classical theory. We already have a fantastic classical theory, but to derive quantum signatures where Planckian dynamics is important. And I think I should stop here. Thank you. Okay, questions welcome. I hope I didn't exhaust you completely. No. Yes. Yes.
So if I understand in chromodynamics, it's kind of a, as you said, it's a kind of a trick, and then
it's not a trick, it's a methodology. Mm-hmm. Trick sounds, yeah.
If one would think about this literally, this spacing in the lattice, one would say, of course, this spacing cannot go into the blank land because then blank scaling, because then it would be something else. Maybe quantum gravity elements will be there. So there is some kind of a a priori agreement between the spacing, energy scale, what we do, where this works. And then we can even let A goes to 0 by assuming that everything else subtle in certain limit that...
Yeah, well, of course, you know, A equals 0 is not, you could argue it's not a physical thing, but, you know, at least you will get, you know, if you say, it just has to be much, much smaller than the length scale at which you want to get kind of universal physics. Yeah.
So there is a kind of interplay of different scales that makes this still meaningful. Okay. Now, and we know when we do quantum dynamics, we don't do quantum gravity. So we will know in which scale and energy scale and length scale.
And they're, of course, much, much, much larger.
Much larger.
Sure.
Now here, if we imitate the chromodynamical way of thinking, then I would say, okay, this is also maybe in some regime and ratio about energy scales and length scales. But there is no way to understand the absolute validity. Yeah. Just like we don't know it from chromodynamics.
Okay.
So
okay.
one can say, okay, maybe there is another scaling where...
Yeah, okay. 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 So the first thing I have to say, you know, when I say our kind of chunks of quantum spacetime are 20 Planck lengths across, this is not just I've put in by hand, but how did I get there? I looked at a specific observable, which was the 3-volume correlator, of which I know from a kind of mini superspace calculation, it has a specific dependence on G Newton. Okay, so I can study. So there is a continuum calculation I can do, at least in some approximation, which is a mini superspace calculation, which computes this. So I can measure the same thing on the lattice. And by comparing these two things, that gives me now a relation between this dimensionful physical Newton constant and one of my dimensionless bare couplings on the lattice. Okay, so this is the thing. So I'm using a specific observable to make the connection. What are lattice units? A priori, they could be anything. And how do I translate them to actual physical units? So this is just one thing to understand. So, and of course, the Planck length depends, of course, on G Newton. Yeah. So let's set h bar and c equal to 1. Then it's very obvious. So the Planck length, and so our this window we can study where we can evaluate the path integral numerically comes with a certain length scale, where the translation comes from, you know, looking at this particular observable. And it turns out that even if we scale around in this big parameter space, it doesn't change the length scale in a very grand way. So a little bit it will change, but not very much. So if you like, with our current setup, where, you know, our computer simulations have a size where you can go to 1 billion blocks or something like this, you are confined, nevertheless, to this Planckian regime. And of course, you're always maybe going further and answering the question. Of course, one always puts in something. So when I say, you know, we are now no longer working with G mu news, yeah, but we are relying on these spaces having still metric properties. For example, if I sit on one of these triangulations, there is a well-defined notion of a geodesic as the shortest path along the edges of the triangulation, like in a graph one would do, you know, between 2 points. And one knows from simpler models where in 2D, which is even much more quantum than this, this maps up to an overall constant on a geodesic notion of geodesic distance in a continuum limit. So one does trust that this is still a meaningful way. Distances I can associate with these microscopic objects, and volumes, they still they survive in the continuum limit, and we have indications that this is so from, for instance, looking at these shape observables. So all of the observables I study, they depend on these elementary length and volume measurements I'm able to do on these very, very singular objects. And really, the proof is in the pudding, of course, that when I make these assumptions and then I do look at specific observables, well, they display a particular behavior. And if I'm lucky, for some, hopefully, I can show that on sufficiently large scales they are compatible with what I would expect from continuum at low energy scales. But they also predict something new, some quantum signatures like this, the spectral dimension is 2. Well, of course, we need now phenomenology to say, yes. So, this is how this would affect, I don't know, our measurements of some light rays that reach us from the edge of the universe. You will see this dispersion relation, and it's directly related to this fact of the spectral dimension. So, yeah, of course, you need to anchor it then in reality. If you come tomorrow with your alternative model, which makes other assumptions, and you make similar predictions, be my guest, and we compare, and we can, even before we run experiments, we can already compare, like, what is your prediction for the spectral dimension, if it's a meaningful question in your framework. But it's such an elementary question, I mean, it's difficult to imagine something even more elementary that would still kind of relate to, space-time, geometry, maybe topology. And then we compare nodes, and if you get the same thing, we say, oh, wonderful, this must be some universal feature, and I like you so much. And clearly your way of thinking about quantum gravity must be some complementary way of reaching there. And of course, there needn't be a single unique way of getting there. But of course, I mean, computability, which I've emphasized here, is really, really important. So how you choose your variable and you deal with all these technical problems of this very, very formal object. Well, we found now one route, where we solved a whole bunch of problems, Wick rotation, conformal divergence, how to deal with the gauge redundancy. But there may be other ways. But really, what I would think of is that, ideally, this is for quantum gravity what lattice QCD is for QCD. So it's not an approach, it's just a way of non-perturbatively computing the path integral. Do we believe in the path integral, and should this still be valid on the Planck scale? Well, come up with something better, but I think this is just so robust and has been just tested, in so many contexts. It's a reasonable assumption, and it's not an exotic assumption to try and push that, all the way where it goes, and it can be pushed to this regime. That's a beautiful message, You can say, this is just so conservative, and I always wanted quantum gravity to be something really, really exotic. Well, we've been there and back, right? And the problem is, of course, once you open the Pandora's box, then you are in this totally non-unique universe of possibilities, and you just don't know even what to compute, and you don't know how to fix the free parameters. Yeah, sorry, that was a long answer to your question. Mm-hmm. Yes. Yeah. This is this famous kind of slicing we introduce. So all our four-dimensional geometries can be thought of as a kind of three-dimensional curved triangulations, where you have a kind of discrete time parameter, which are called tau in some of these formula. So it's tau equal to 1, tau equal to 2, tau equal to 3. So and by virtue of having this parameter there, you can enforce, and by four simplices, connect from one layer to the next. And they're, of course, very irregular, and so this looks like flat slices, but of course the slices are not flat. So I have this parameter, and what this time notion allows me to do is to enforce the absence of outgrowth. So it, if I didn't have such gluing rules, things like this would be allowed. This is my kind of initial geometry. Let's say it's a 3-sphere, and this is my final geometry, also 3-sphere. But if I now would impose some kind of notion of time on this, you would see that generically space would fall into several disconnected components. So that is a kind of spatial topology change would be naturally part of that. So what I'm doing is by hand, I say, here's a branch point. I disallow such branch points. And you could say, well, who tells you, right? I mean, the path integral, we should sum over everything. Well, we started out, of course, in the Euclidean quantum gravity effectively by including all of such things. And no one has been able to make sense of the superposition. I mean, really following exactly the same argument otherwise, which I gave you, on these objects that contain these branches. And of course, you could have even wilder things, right? You could allow, holes in there. I mean, non-trivial topologies. And then, of course, you have, even in 2D, you don't have a well-defined way of summing over all of these topologies because they are just, so countably many of them that, well, forget about the path integral. Yes. Mm-hmm. Okay. Okay. Yes. Mm-hmm. Yes. Mm-hmm. Right. Right. Mm-hmm. 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 Yeah, of course. By continuum, I don't mean continuum in the sense of classical GR. I should make clear. Mm-hmm. Yeah. Yes. Mm-hmm. 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 Yes. Yeah, yeah. No, it's a bunch of very good questions. Let me try and be brief. So the philosophy is not that there is a fundamental length, which is kind of the Planck length, because it comes with these, non-uniqueness issues. Okay. So therefore, I adopted this more like standard critical systems language by which. Yeah, I mean, whatever. At least de facto, your lattice spacing should be much, much smaller than the scale of physics you're interested in, which in this case is the Planck length. We cannot. So factually, our computation, we cannot resolve the Planck length. We can only resolve something that is maybe 3 or 4 or 5 Planck lengths. So really, you could say I'm not doing genuine Planckian physics, but I think we're getting a good idea that trivial stuff happens already at 10 Planck lengths. So that's what I was talking about. So what is the continuum limit? I think, yes, so one shouldn't imagine that this is a formalism that reproduce in whichever way arbitrary solutions to the classical Einstein equations. No, it just cannot do this. It's just, even the questions you can ask in this regime, tend to be very different from the questions we ask in GR. In GR, we're looking at solutions, right? We look what happens close to the horizon of the black hole. And for us, the horizon is this thing, right, at R equal to where we're sitting at a radius of 2 gm, right? Which of course, again, there's not a physical thing here. So this is a very geometric setup. You can only ask questions that are genuinely diffeomorphism invariant, and there are no natural frames of reference in this regime. There is no tensor calculus. So the question is then, in a way, what is quantum gravity, and what do I expect it? How do I expect it to be characterized? I would say, in this very non-perturbative regime, if you're lucky, we can characterize it by certain universal, say, scaling coefficients. Yeah, like you do in condensed matter, in strongly correlated condensed matter systems. For instance, as I was talking about, the correlator. Yeah, maybe I can extract some universal scaling parameters, and that's the most I can hope to do. I'm not able to say something to test the equivalence principle at the Planck lengths, because I can simply not, this little elevator I would like to drop this is operationally not defined in any way, not even remotely. I mean, by so many tens of orders of magnitude. So therefore, my health warning, this is a very different regime. But of course, if you come from my angle of things, and if you look at the long wish list that people have who don't have functioning computational frameworks, what they want, all the questions they want quantum gravity to resolve, I would say most of them are, of course, utterly unrealistic, because they will not, if you take, quantum space-time foam, kind of seriously, if you really say, okay, we have to go beyond perturbations here, what is this thing there, this substance, who knows? So if one takes that seriously, then one cannot say at the same time one shouldn't trust all these, long wish lists, because then it's something like that. Maybe more resembling, in terms of the setup, a strongly interacting kind of meta system. But of course, we're talking about fundamental physics. So in the end, it better don't be, very many arbitrary parameters that appear here. So, but it's a really different outlook. Yeah. Yeah. Yes. Yeah. Yeah. It's a technical statement that, I identified my physical and lattice length scale in a certain way, and then we find that you can ask, what is the edge length here? Yeah. So this corresponds to maybe 2 Planck lengths. In theory, but in practice, really, I mean, it's a finding. It's a finding that, well, maybe this is on the order of a Planck length, maybe in our simulations, or maybe of the order of 2 Planck lengths. Maybe Danny knows better. Yeah, but of course, in this lattice setup, you don't trust any results on the order of a single lattice spacing, because they are maximally sensitive to your lattice artifacts. No, there is. I've made an explicit identification that comes from making an experiment, from measuring a certain correlator, which gave me an explicit relation between what are lattice units and how should I interpret them of dimension full, physical length units. And from those, I now understand, my 1 million building block lattice is just 20 Planck lengths across. And then, of course, if I translate it to the individual distances, right, taking the full square root, etc., then it will work out nominally to something like an edge is on the order of the Planck length. Yeah, yeah. No, but your coarse graining is not my coarse graining. My coarse graining is, yeah, of course, making the lattice finer, but I have then to look how my couplings renormalize under this way. And that has already been taken into account when I make this identification. So this statement I'm making is already in the A to 0 limit. I'm extracting this relation. So any physical statement one makes here is already one that pertains to the nominal A to 0 limit. of course, you cannot take this on the computer, but you systematically study the dependence on A, and then, you know, only certain things that have a clear, you know, functional behavior as a function of this A, which you can identify, then you say, okay, if I now would extrapolate this to A equal to 0, it's this. And this, when I talk about a result or, you know, a dimensionality, strictly speaking, this is what I believe will be true in the A equal to 0 limit. And then once you have that, you can ask, in addition, how does this thing look at a certain length scale, right? That could be, if the total thing is 20 Planck lengths across, you can ask, well, how does the behavior at 10 Planck lengths differ from that at 20 Planck lengths? That you can still ask after you've taken the continuum limit. So one has to be careful with the coarse graining. So here's a coarse graining, you could say, is really just a technical step. And the only thing I can trust is things that survive in the A to 0 limit, and that's what I'm talking about. And that's what lattice, by a mechanism called finite size scaling, that's what lattice simulation extract. Correct. Yeah. Yeah, very good. Of course, that's right. That's right. No, no, no. It's a QFT. It's a QFT logic where you, of course, you know, well, who invented it? Was it QFT or was it the condensed matter people, right? That's a very old-standing argument. But indeed, of course, you know, in QFT, this A is just the cutoff you put in by hand, and that's your regulator. And in the condensed matter system, it's a physical thing, you know, it's whatever, you know, the diameter of the atoms or whatever, yeah. Very good. So in standard QFT, of course, you're sitting on Minkowski space, and you have Fourier transformation. So you have a direct relation between distances and momenta. So indeed, there it translates in an immediate way to an energy scale. But of course, we know in GR already classically, of course, what energy is of course a very, very tricky question, right? And of course, it's not a conserved quantity in GR because you have time-dependent phenomena. So there is this immediate, as soon as you go away from flat space, I would say, even if you go to something like de Sitter, well, you don't, you know, translation to momentum space becomes very non-trivial. So if you ask what's the mass of a particle in de Sitter, that is not it turns out it's not a very well-defined question. And this is far beyond this, of course, right? These are general curved quantum fluctuating geometries. So we are really sticking, if you like, to a real space picture where, yeah, length variables are meaningful still. Length measurements and volume measurements are meaningful. But what would be a natural notion of energy? That's, I don't dare to say. Yes.
Can I interpret it as some sort of, maybe not energy, but some other quantity, some resource that you have in your laboratory?
Why are you not happy with it being a length scale?
No, I'm happy. I just want to make sure I understand.
It's my best resource, but of course it's in a way it's a fiction, right? It's a part of this formalism and where I set things up. But in the end, as you're saying, dependence on A will just drop out. Yeah, and will be reabsorbed. Of course, it dictates also typically how my bare coupling constants get renormalized. I mean, you know, powers of A will come into renormalization and making certain things finite. So that's also where A comes in. But once this has happened, in the end, you know, that's even in QCD, you come out with a description of relations between dimensionful quantities. And for instance, QCD, the only thing, you know, that it depends on is a single scale, is lambda QCD, which gives units to everything else in the picture. Yeah. I mean, how far can we push these classical concepts? Of course, yeah, you know, I would say 95% of all research in quantum gravity relies, of course, on perturbative semi-classical notions, and that this G mu nu will be, you know, even a meaningful concept at trans-Planckian energy. I would say this is madness, but okay, you know, you can just formally push things. You know, your paper will not scream when you write it down. I don't know what ChatGPT says. Probably it also will not scream at you. Okay. Yes. Yes.
I'm very interested in this, how we implement diffeomorphism invariance.
Yes. Yes.
If I understand correctly, the remnant is relativity, basically, of the...
It's not a remnant. It's more like, you know, that's right. That's right. That has the same function as...
And do I understand correctly, you consider all possible relabelings? You're not restricting to a subclass that preserves some structure. You really allow for all possible relabelings.
Well, the thing is, well, you know, you can write down your path integral over, of course, if it's a finite system, over label triangulations. And I said, these are the things in the computer. Yeah, but the relabeling is really, you could say, a passive relabeling of elements that are kind of distinct. And really generically, if you have n building blocks, really the size then of this relabeling group is n factorial. And there is no structure to be preserved a priori, because what structure do you want to preserve? And really the physics is, of course, in the unlabeled objects. Yeah. And of course you're putting certain things in, but so this is basically, you know, a democratic sum. Yeah, because apart from this thing, which is almost always 1, as I told you, it's just e to the, well, either I as graph, right? So each geometry really contributes with their weight here. But of course, what plays a role in bringing about this non-perturbative dynamics on the lattice is how many with a given weight contribute. So you get kind of a measure term or an entropy term, you know, how many are there for a given value of the action? And it turns out in the regime where we see interesting non-perturbative physics, these two terms are in competition with each other. So it's really kind of entropy energy effects, which one might also be, you know, which appear in condensed matter systems also. But kind of the entropy really comes from the number of states that then contribute with a certain weight. And depending on how you tune your bare coupling constant, you know, you enhance, of course, certain properties of these geometries or other, you know, or not. So there are also regions in phase space which clearly have no physical interpretation at all, because by forcing the parameters, for instance, to be, you know, to be this kind of inverse Newton constant to be very large, you are putting yourself in a regime where conformal kind of degrees of freedom are very much enhanced, and they let your path integral degenerate in very bad ways, which means it doesn't have a 4D interpretation at all, as far as we understand. So you can drive the system really into regions where there doesn't seem to be any meaningful physics, at least gravitational physics associated with it.
So one last thing on computability.
Yes.
So one of the strengths or successes of QCD was to, well, compute things. And in that case, that could be directly tested then at
Exactly.
so
Exactly.
masses, Feb's causation, so on.
That's right.
So in the view of people nowadays see the universe as a
Yeah.
collider experiment, is there any hope that you could have, for the early universe, a similar view that basically we have, given the length scales that we have, gives you an idea of the time scales during which then really very unique phenomena could actually occur, and whatever particles, but I don't know, we could look for. So how unreal?
Yeah. So yeah. It's a very long way. Where I said, you know, I claimed, well, we have a roadmap to get there. For instance, from the study of 2-point correlators. You see, of course, you know, the way we think about the early universe nowadays is we are putting by hand, saying, well, it will be kind of de Sitter-like. with small quantum fluctuations that are typically seeded by an extra scalar field I put in by hand. This is just the inflaton field. And then, you know, they kind of then the underlying almost locally flat spacetimes then inherits these. And, you know, so, but, yeah. So my question is, can I go one step back and come up with saying, look here, I've calculated a fluctuation spectrum in this very non-perturbative regime. Is there any way I can verify or falsify these assumptions one typically makes for the early universe, which are, you know, I can say they're not well motivated, but they're pulled out of a hat. You see, they're not derived from something more fundamental. So, and the idea is maybe we can go one step further back and do derive, you know, something like some properties of this fluctuation spectrum. And then again, of course, on top of that is then a big question, you know, would this survive? You know, how does it express itself? Would such a signal even survive to nowadays, what we can observe nowadays? And then we're sitting in the same boat as everyone else who is looking for, you know, quantum signatures. But this seems to me the most realistic way, and that's why we're very much pushing this. But it is very, very non-trivial, let's say, measuring it, and also really conceptually, these endpoint functions are these very global objects, and well, they're very hard to measure. They're very hard to measure to get clean signals. Yes. Yes. Mm. Mm-hmm. Yeah, what I would say, of course, it comes as a package, and you could say, which we've taken over as a methodology. And it has this beautiful feature of, you know, forgetting all the discretization details and therefore satisfying uniqueness. There may be other possibilities, but then you have to argue also how this uniqueness issue is being resolved, if that's your picture. Yeah, I'm not excluding that there are other scenarios, but yeah, how do you resolve this? Then I don't know. I should say Danny is here the local expert on CDT simulations for those who don't know him. Yeah. Okay.
Thank you very much.
Pleasure.